Let's investigate a set of quantum-resistant cryptographic algorithms called CNSA 2.0. CNSA means Commercial National Security Algorithm Suite. CNSA 2.0 only includes algorithms that are classified as quantum resistant. If we use the term quantum resistant, or QR, that is equivalent to saying quantum safe, or QS, and it's also equivalent to saying post-quantum cryptography, PQC. So QR, QS, and PQC all refer to cryptographic algorithms which are not vulnerable to quantum cryptanalysis. Let's see which cryptographic algorithms are included in CNSA 2.0. In this suite of algorithms, we have ML-KEM-1024. ML-KEM means Module Lattice-Based Key Encapsulation Mechanism. This number, 1024, specifies the parameter set. ML-KEM is a name that appears in FIPS 203. FIPS means Federal Information Processing Standard. ML-KEM is the current name, but there was another name that was previously used. And I'll write that name underneath. It is Kristall's-Kyber. So Kristall's-Kyber with a K. So Kristall's-Kyber was the name for an earlier version of ML-KEM. And now this descriptive acronym is used. That is the name that appears in FIPS 203. And this algorithm has the purpose of key establishment. So we're going to do key establishment using this module lattice-based key encapsulation mechanism. And we need to use the parameter set that is specified by this number 1024. CNSA 2.0 also includes ML-DSA-87. This means Module Lattice-Based Digital Signature Algorithm, and 87 specifies the parameter set. ML-DSA is the name that appears in FIPS 204. So over here we have the name that appears in FIPS 203, and over here we have the name that appears in FIPS 204. There was also another name that was previously used for an earlier version of ML-DSA. And the name is Crystals Dilithium. So we have dilithium. So over here we have Kristall's-Kyber, and over here we have Crystals Dilithium. Now these have been renamed to ML-KEM and ML-DSA. So these acronyms are descriptive, and they're followed by a number which specifies the parameter set. So we have an algorithm for key establishment, and we also have an algorithm that can allow us to do digital signatures. Both of these are public key or asymmetric algorithms, and they are classified as quantum resistant. We can also call them post-quantum cryptographic algorithms. Now, CNSA 2.0 also includes LMS and XMSS. LMS means Leighton Macaulay signature. XMSS means Extended Merkle signature scheme. Both LMS and XMSS are stateful hash-based digital signature schemes. So it's important to emphasize that they are stateful, and these are hash-based. So they are not lattice-based. ML-KEM and ML-DSA, these are module lattice-based public key algorithms. But LMS and XMSS, they are hash-based. And they have a special intended purpose. So both LMS and XMSS are intended for software and firmware signing. So that's their intended purpose. And they're also a type of digital signature algorithm. So you can use LMS and XMSS for digitally signing software and firmware. And ML-DSA, that is a general purpose digital signature algorithm. And CNSA 2.0 also includes some cryptographic hash functions. We have SHA-384, as well as SHA-512. So when you see this acronym SHA, that stands for Secure Hash Algorithm. And SHA is specifically referring to SHA-2. So that is a family of secure cryptographic hash functions. So this secure hash algorithm is actually SHA-2, and this number that comes after specifies the output length. You can think of this as the message digest. So this is 384 bits, and over here we have 512 bits. So when you see SHA by itself, that is referring to SHA-2. But there is also SHA-3, and that will be specified with a 3 over here. And then you will see a number, and that specifies the message digest length. We can think of this as the output length of the hash function. So this is what is used for cryptographic hash. And this CNSA 2.0 also includes the symmetric block cipher AES with 256-bit keys. So this is symmetric. AES is symmetric. It's a symmetric block cipher. Up here, ML-KEM, ML-DSA, and these two hash-based signature schemes, they are asymmetric or public key algorithms. That is different from AES. AES is symmetric. That means there's only a secret key, or you can think of it as a private key. So there's no pairs of keys. Up here, for these public key algorithms, there's a public key and there's a secret key. They come in pairs. But over here, we're only dealing with a secret key. That's why this is called symmetric. AES stands for Advanced Encryption Standard. And there's also another name that is sometimes used, and that is Rijndael. It is spelled R-I-J-N-D-A-E-L. So Rijndael. That is another name for Advanced Encryption Standard. And we specifically want to use 256-bit keys. So you can see the naming convention is very reasonable. You have an acronym, which is descriptive. It describes what's going on with this algorithm. And then you have a number, which either specifies the parameter set or something to do with how to implement the algorithm. So these are very descriptive names. But it's also useful to keep in mind there were some previous names like Kyber, dilithium, and Rijndael. So this is CNSA 2.0. These algorithms are included in the Commercial National Security Algorithm Suite. But there was a previous version, CNSA 1.0, which included some algorithms that are not quantum resistant. They are actually vulnerable to quantum cryptanalysis. And we're going to see them over here. So previously in CNSA 1.0, there was the algorithm ECDH. That is elliptic curve Diffie-Hellman key exchange. And the purpose of this algorithm is also key establishment. So it's just like ML-KEM. But there's a slight difference. ML-KEM is a key encapsulation mechanism. That's why we have this KEM part in the name. But elliptic curve Diffie-Hellman key exchange is a non-interactive key exchange, or NIKE. So that is ECDH. And there's also elliptic curve digital signature algorithm. So this is elliptic curve cryptography. ECDH, that is for key establishment, and ECDSA, that is the elliptic curve digital signature algorithm. And both of these algorithms, ECDH and ECDSA, they were intended to be used with the curve P384. So this is like specifying the parameter set. So just like how we have these numbers over here that specify the parameter sets, we also need to specify which curve we're using, because this is elliptic curve cryptography, or ECC. And elliptic curve cryptography is based on the elliptic curve discrete logarithm problem. And that's a special case of the generalized discrete logarithm problem. And that's the reason these are not considered quantum resistant. So they are based on some computational assumptions, and those computational assumptions make them vulnerable to quantum cryptanalysis. Now, there's also some other algorithms that were previously included in CNSA 1.0. So they are Diffie-Hellman key exchange. So we have the DH over here, but this is not an elliptic curve cryptographic algorithm. And we also have RSA. So all of these acronyms over here, they are referring to the algorithm, like KEM, that's key encapsulation mechanism, DSA, that's digital signature algorithm. But these acronyms over here, they're actually referring to the names of researchers that wrote some papers that led to the standardization of these algorithms. So over here we have Diffie and Hellman, and RSA, that is Rivest, Shamir, Adelman. So both Diffie-Hellman key exchange and RSA, they were intended to be used with a minimum 3072 bit modulus. That's the minimum size of the modulus for both RSA and Diffie-Hellman key exchange that was allowed in CNSA 1.0. So you can see how I've organized these guys. We have the algorithms that are responsible for key establishment, and then we have the algorithms that are responsible for digital signatures. And note that RSA can fit into both of these categories, because you can adapt RSA, you can make it into a digital signature algorithm, and you can also make it into a key establishment algorithm. So RSA is based on the hardness of integer factorization. But integer factorization is related to order finding. This is an insight in Shor's algorithm. And order finding is actually closely related to the generalized discrete logarithm problem. So both of these types of problems make these algorithms vulnerable to quantum cryptanalysis. So the computational assumptions that underpin the security of these algorithms, they make them vulnerable to quantum cryptanalysis, and specifically Shor's algorithm. So that was an insight from Peter Shor. And that's why these are no longer included in the commercial national security algorithm suite. So in CNSA 1.0, they were still present, but now in CNSA 2.0, they've been deprecated. So there's a transition going on from these algorithms over to these lattice-based and hash-based algorithms. So notice that all of these vulnerable algorithms, they are public key algorithms. So a cryptographically relevant quantum computer, CRQC, can run algorithms that specifically target these public key algorithms. So that is quantum cryptanalysis. And you can see that elliptic curve Diffie-Hellman and elliptic curve digital signature algorithm, they form a nice pair. So just like ML-KEM and ML-DSA. There are slight differences. This is a key encapsulation mechanism. This is a non-interactive key exchange. But overall, you have algorithms that can do key establishment and algorithms that can do digital signatures. And we need these algorithms to be part of protocols. That's why it's really important to have a set of quantum-resistant algorithms. Now, these are not the only algorithms that are classified as post-quantum cryptography, but these have been standardized. So we have these module lattice-based public key algorithms, and we also have these hash-based digital signature algorithms. So over here, these first 3 rows, they're all public key algorithms. Then we have these cryptographic hash functions, and then finally we have a symmetric block cipher. So this algorithm is symmetric, and up here we have asymmetric or public key algorithms. So in other videos, we're going to explore the details of how to implement these algorithms. We're also going to explore how quantum cryptanalysis works and how you can perform quantum cryptanalysis using a cryptographically relevant quantum computer.